In this fifth and last video of chapter 1, I want to talk about convergence to the steady state of the Solow model. This notion of convergence is an important one, and it deals with how the economy moves from any state of the economy to the final, let's say, steady state, where the economy doesn't change from one period to the next one. In this video, I want to do two different things. First, I want to properly introduce this concept of convergence in a dynamic economic model. And second, I want to prove the fact that convergence happens in the augmented Solow model. And in order to make the proof a bit simpler, I will use the case of a Cobb-Douglas production function. First, let me give a definition of this notion of convergence. So we'll start by introducing any dynamic economic model, which is described by a state variable that we will call x, and this economic model is dynamic, meaning that the evolution of the system can be described by a law of motion. So x t plus 1 is some function of x t, whatever the time period. And in this dynamic economic model, we'll say that the economy converges if starting from some initial state, which we call x0, the economy ends up in a steady state as time goes to infinity. So mathematically, this writes that limit of xt as t goes to plus infinity is equal to some value x star. So convergence here means that the economy starts at x0, moves to x1, x2, and so on, and finally, if we wait sufficiently long, the economy ends up in a steady state. Now, as I said, we'll prove that convergence happens in the augmented Solow model. So in order to do this, I'll first remind you of the dynamics of the state variable of the augmented Solow model, which is k tilde. So as a reminder, in the augmented Solow model, population L grows at a rate n, which is fixed, and technology A also grows at a rate g. And we have this law of motion for a capital per efficient worker, k tilde t. The variation of k tilde t is due to savings and is due as well to capital depreciation and dilution. At steady state, the variation in k tilde is equal to 0, which means that savings are equal to the capital dilution and depreciation effect. So now that we have the dynamics of the augmented Solow model in mind, the challenge is to prove that starting from any state of the economy, k tilde t, we will always end up in the steady state as defined before, k tilde star. In order to do this, we're going to use two different tricks, let's say, which I will introduce once we need them. The first trick is to write the law of motion for k tilde t and divide this law of motion by k tilde t itself. So the first line of computation that you have here is delta k tilde over k tilde is equal to sf of k tilde divided by k tilde minus n plus g plus delta. This expression can be factorized by n plus g plus delta, and you get the following result on the slide. We'll need to record this first result as equation number 1. Now the second trick that we'll use in the computation is the characterization of the steady state, which is sf of k tilde star is equal to n plus g plus delta times k tilde star. Again, we can divide this equation by k tilde the star, so that we get that n plus g plus delta is actually equal to s f of k tilde star divided by k tilde star. Now, this last result can be plugged in back in equation 1, so that I replace the n plus g plus delta on the denominator inside the parenthesis by f of k tilde star divided by k tilde star. So we get this quite important expression in terms of convergence. The growth rate of variable k tilde t, so delta k tilde t divided by k tilde t itself, is equal to n plus g plus delta times a ratio between f of k tilde over k tilde in the current period at time t, and the same ratio at the steady state, minus 1. Now we need to make sense of this formula in the case of the Cobb-Douglas production function, where f of k tilde t is equal to k tilde t power alpha, which means that f of k tilde t divided by k tilde t is equal to k tilde t power alpha minus 1, so that you get the formula that you can see on the slide. Now, an important point is that the alpha parameter is smaller than 1, so that alpha minus 1 is actually negative. This is important because if we are in a situation in period t where k tilde t is smaller than k tilde star, then of course the ratio k tilde t divided by k tilde star is smaller than 1. But because alpha minus 1 is negative, the whole fraction elevated to the power of alpha minus 1 is bigger than 1, so that everything which is inside the brackets is actually positive. And because this is positive, this means that the growth rate of k tilde t, which is on the left-hand side of the equation, is actually positive itself, so that we get the following result. If in any period t we are below the steady state, then the growth rate of the variable is positive, and conversely, if at any point in time we're above the steady state in terms of k tilde, then the growth rate of that variable will be negative. So that whatever the initial situation, we always move in the direction of the steady state. What's more, the result also shows that as long as you haven't reached the steady state, you keep moving towards it, which is a proof of convergence. An important property as well that we can find useful if we apply this theory of the Solow model to actual countries is the fact that the growth rate of k tilde, so delta k tilde over k tilde, is bigger when k tilde t is small, because then when k tilde t is small, the fraction k tilde over k tilde star is small as well, so that we get a big growth rate here. So the convergence happens at a slowing rate as we approach the steady state. As k tilde t becomes bigger and bigger and closer to k tilde star, then it will move slower and slower. One last thing which is really important in terms of interpretation is the fact that convergence is conditional and not absolute. It is conditional because the convergence, this whole formula, depends on delta, g, n, s, and k tilde star. So if you have two different countries with different values for these exogenous parameters, then these two countries won't converge at the same speed, they won't converge towards the same steady state, and so on and so forth. So convergence doesn't happen necessarily between two different countries towards the same steady state. So this is the end of the final video of this chapter 1. So make sure you've understood properly the concept of convergence towards a steady state, and as well have an idea of the proof of how to show that convergence actually happens inside the augmented Solow model. As usual, feel free to ask any questions you might have either on Moodle or at the end of a lecture.